In this video, we are going to calculate the area between curves. We're going to determine the area of the region bounded between two curves by integrating with respect to the independent variable. We're going to find the area of compound regions, and then we're going to determine the area of the region between two curves by integrating with respect to the dependent variable. So we'll start by finding the area between two curves. Here's the theorem. It says, let f and g be two continuous functions in which f of x is the upper function, g of x is the lower function in some interval from a to b. Let R be the region let R denote the region bounded between the graphs f of x and g of x, and to the left and right of x is equal to a and x is equal to b, respectively. Basically, the area between the curves then is going to be the definite integration from a to b of the upper function minus the lower function with respect to x. If we are finding the area between the curves in which we are doing the integration with respect to y, then the things that change is that we call this from c to d of the most right function minus the most left function with respect to y, so dy. So, as an example here, we have the upper function, which is the g of x, in this case is the upper function, and the lower function would be the f of x because it is the one that is on the lower portion from -2 to 2, if that was where I was integrating. So if I wanted to find the area between the curves between -2 to 2, g of x would be the upper function and f of x would be the lower function. And if I were to integrate with this, I would absolutely, just because of symmetry, integrate from 0 to 2, and of course, multiply the answer by 2. So, they're asking us to determine the area region between the two curves in the given figures, or by integrating over the x-axis. So I'm going to integrate from 0 to 2 because this side, by symmetry, equals this side. So I'm just going to go from 0 to 2. My upper function is my g of x in this case. My lower function is my f of x in this case, dx. So this is going to go from 0 to 2. My upper function is 1. My lower function is x squared minus 3 dx. And so I'm going to have from 0 to 2 of 1 minus 3, so 4 minus x squared dx, which gives me 4x minus 1/3 x raised to the 3. Evaluated, oh, don't forget my 2, because we have two sides, so don't forget my 2. And symmetry, evaluated from 0 to 2. So I have 2 multiplied by 4 multiplied by 2 minus 1/3 multiplied by 2 raised to the 3rd, and then minus 0. That's kind of nice. So I end up with 2 multiplied by 8 minus 8/3, and my final answer is 20 over 3, or 10 2/3, or 10.6 repeating. Depends on if they want exact or approximate. The exact, of course, is either this form or this form. This is an approximate. All right, let's take a look at my next one. For my next example here, I don't have a picture, so I'm not really sure without doing a graph of, first of all, where they cross, and second of all, who is the upper function and who is the lower function. Now, I happen to know that when this is negative, it's going to have, when the leading coefficient on the x squared is negative, it's going to be a parabolic shape opening down. So I do know that it is likely that the negative x squared plus 18 is probably the upper function, but without knowing, I'm going to just do a quick sketch of each one of these. Factoring the negative out, so I have negative x, will factor out, leaving me x minus 18. Then this tells me that this graph is going to be a parabolic shape that's going to cross at 0 and at 18. And it's a negative coefficient, so it's going to look something like that. My y is equal to x squared. Well, that's a quadratic. That's going to look something like that. So you can see that this is my upper function, so I'm going to call that f of x. This is my lower function, so I'm going to call that g of x. And the two places which are crossing is at 0, and then I just had to figure out where the other location of crossing. So I set these equal to each other. X squared is equal to negative x squared plus 18x. Bring everything to the left, so I have 2x squared minus 18x is equal to 0. Factor it out of 2x, and I get x minus 9. And that kind of confirms that I'm going to be crossing here at 0, so that my lower bound is 0. My upper bound right here is where they cross, is at 9. So my upper bound is 9. So I'm just going to erase this. And so my integration then is the integration from 0 to 9. My upper function was the negative x squared plus 18x. My lower function was the x squared dx. So this is the integration from 0 to 9 of negative 2x squared plus 18x dx. This then becomes negative 2/3 x raised to the third plus 9x squared, evaluated from 0 to 9. And when I get done, this becomes 243. Now these are units of area, so we should have units squared on all of these because it is an area, so it'd be units squared, whatever the units are. We have the cosine of x, and y is equal to the cosine squared of x. Again, I'm not really certain who is above and below, or if it happens more than once, so they could change position. Now the cosine wave from negative pi to pi will, actually let me do it this way. The cosine wave will cross at pi halves and negative pi halves, and then at pi, negative pi, and pi, it's going to look like this. So this is what the cosine wave looks like. So here's my cosine wave. Here's the cosine of x. Now the cosine squared means that I'm going to have a graph that looks like this. At most, it's going to be at 1. So at x is equal to 0, will be at 1. At x is equal to pi will be at 1. At x equals to negative pi would be 1, because I'm taking my answer and I'm squaring it. So I'm going to end up with the graph that's going to look something like this. It's going to come down. It's going to come up. It's going to come down. It's going to come up. And so you can see that it does have symmetry, so I get to use the symmetry. But I also have this area in which, so I'm going to have this area from 0 to pi halves, multiplying by 2, so I get both sides. My upper function is going to be the cosine of x. My lower function is going to be the cosine squared of x, and dx. But then here in this region, right, my cosine squared is going to be the upper function. So then I'm going to have plus 2, and this integration is going to go from pi halves to pi. Now my cosine squared is the upper function, and my lower function is the cosine of x dx. And probably going to use some power reduction formulas for the cosine squared. So remember that the cosine squared of x is the same thing as 1/2, 1 plus the cosine of 2x. So we'll probably use some power reduction formulas and integrate in that form. When I get totally done, by the way, by doing these two integrations, my final answer is the sine of x, the sine of x minus 1/2 x plus 1/2 the sine of 2x. And this one will be evaluated from 0 to pi over 2. Oh, and don't forget we are multiplying this thing by 2 because we have the left and the right side. So multiplied by 2, and then plus 2, and then 1/2 x plus 1/2 the sine of 2x minus the sine of x, And this one gets evaluated from pi halves to pi. And then from there, you should be able to evaluate that. So I'll leave that to you. Now let's take a look at D. With D, I have e to the x, which is going to look like this. This is e to the x. And then I'm going to have e to the negative x. So this is e raised to the negative x. And I'm going to go from -1 to 1. So from -1 to 1. And so the area that I am looking at would be, if I bring these up here to here, the area I'd be looking at would be this. So you can see that I have symmetry again, so that all I have to do is integrate 2 times the integral of, I'm going to go from 0 to 1. Now my upper function is going to be e to the x. My lower function is going to be e to the negative x. And dx, nice easy integration, so I'll leave that up to you to finish. Now, when we're looking for the area of a region that crosses curves, then it's like the one that I did up above with the cosine and cosine squared. So the first thing you're going to want to do is graph it, if you can. A very quick little sketch of a graph. And then you need to figure out where they cross each other. And so what you do is you set them equal to each other and see where they cross. So I have x squared plus x is equal to x to the third. Bring in x to the third, or actually bring everything to the right-hand side. I have 0 is equal to x to the third minus x squared minus x. Factoring out an x, I'm going to get x squared minus x minus 1. And so you can see when x is equal to 0, which is right here. And then the second one, I'm going to have to use a quadratic formula. And so when x is equal to the second crossing, which is right here, I'm going to set this using the quadratic formula. So I have -1 plus or minus the square root of -1 squared minus 4 multiplied by 1 multiplied by -1, all divided by 2. So the second place in which this will cross is 1 plus or minus the square root of, and I end up with 5 over 2. All right. So I now have my three limits. Here is 1 minus the square root of 5 over 2, and this one is 1 plus the square root of 5 over 2. And so I would integrate this starting with 1 minus the square root of 5 over 2 to 0. And in this region, the x to the cubed is the upper function, and then so it would be minus the x squared plus x dx. And then I would have plus the integral from 0 to 1 plus the square root of 5 over 2. And in this region, the upper function is the x squared plus x. The lower function is x to the third dx. And after that, it's not too bad of an integration, so I'll leave you to it. On B, what we're going to do again is draw a quick little sketch. I have 12 minus x. So this is just the line y is equal to 12 minus x. Its intercept here is at 12 and it has a slope of -1. My other function is from y is equal to x, the square root of x. So y equals the square root of x would look like this. Y is equal to the square root of x. And then my last part, my last function is that y is equal to 1. So then I have this line y is equal to 1. Y is equal to 1. So what I'm trying to find is this really small region. So let me just make this region a little bit easier to see. So this is y is equal to 1. And then I have this square root of x. And then I have this line here. So you can see in this region, the upper function is the square root of x. But in this region, the upper function is that line 12 minus x. So what I have to do is I have to figure out where each one of these are crossing so I can find my limits of integration. So the first thing I need to do is find this value. And this one's pretty easy. I just set 1 is equal to the square root of x, and so we know that x is equal to 1. So I know when x is equal to 1, I'm going to start the integration here. I also can find this point fairly easy. This is just simply going to be 12 minus x is equal to 1. And so I'm going to get 11 is equal to x. So I have that one. This is my final x value that I'm going to need. So that is the place in which the square root of x is equal to 12 minus x. And then this just is a matter of squaring both sides. And so I get x is equal to 144 minus 24x plus x squared. And so I'm going to get 144 minus 24x. Actually, when I subtract one more, that'll be 25x. 25x plus x squared. And that's going to be equal to 0. And this factors into, let me see, I have 16 minus x and then 9 minus x. So my answers are 16 and 9. Now you do have to go back and check, and you can see that when you put in 16, this is an extraneous solution. So even though you have a solution, you have an extraneous solution. So my last place in which this crosses is when x is equal to 9. Now to set up my limits, to set up my integration, my first integration is going to be from 1 to 9. And in this region, the square root of x is the upper function minus the lower function, which is 1 dx. And then I'm going to integrate from 9 to 11. And in that region, the 12 minus x is the upper function, and my lower function is 1 dx. And I'll let you finish that one off. My last one is sine cosine. And so I know what my sine wave looks like, and I'm going to go from negative pi to pi. So here's pi, here's negative pi. My sine wave looks like this. Here's my sine wave in that region. Here's the sine of x. My cosine in this will look like this. So you can see that I have this one and this one are the two places in which I am crossing. And if I'm not sure how to solve this, I would set sine x is equal to the cosine x. And this happens when I am at negative pi fourths. I just look at my unit circle, so negative pi fourths and negative 3 pi over 4. So I'm going to go ahead and set up the integration. So I'm going to integrate the first piece from negative pi to negative 3 pi over 4. And in that region, my sine wave is above the cosine wave. It takes care of this region. And then I'm going to add to it the integration from negative 3 pi over 4 to pi over 4. And in that region, I have the cosine wave is going to be above. So that's the cosine of x minus the sine of x and dx. And that takes care of this region. And then I have my final region, which is going to be the integration from pi over 4 to pi. And in that region, the sine wave is the upper function. And then that's it. And I'll leave that to you to go ahead and solve for that. Now, if we can integrate with respect to x, we can definitely integrate with respect to y. And this is the theorem that allows us to do that. When we're looking at this theorem, the u is the one most right, the v is the one most left. And then we go from c to d, and these are the limits on the the y-axis. So if I was asked to find the area between two curves, and it's functions of y this time, not functions of x, then this would be the lower bound and this would be the upper bound. This x is equal to 9. In other words, just 9 is my upper function, and in this region, the y squared is my lower function. So I know that I'm going to integrate from -3 to 3. My upper function is 9. My lower function is the y squared. And I say upper and lower loosely. It's really the right and then the left. Now you can know that because of symmetry, I can really do 2 multiplied by 0 to 3 of 9 minus y squared dy. And I'll leave you to that. For my next example, we can see that y is my most right function. That's this. Y is my most right function. And y squared is my most left function. So again, I'm going to integrate from 0 to 1. My most right function is y. My most left function is y squared dy, and I will leave you to that one. With c, I don't have the graphs, so I could go out to Desmos and graph this. I also know that this is x is equal to 2y, and if I were to solve for x, I would have 1/2 x is equal to y, which means it has a graph that looks like this. So this is x is equal to 2y. And then this is the same thing as y squared minus 1. This gives me y minus 1, y plus 1. And so I'm going to cross at 0, I'm going to cross at -1, I'm going to cross at +1. And so it's going to look something like this. It's kind of like a regular old polynomial, but on its side. And so I need to figure out where these are the upper and lower functions. And again, what I'm going to do is I'm going to set them equal to each other. So I have 2y is equal to y cubed minus y cubed minus 3y is equal to 0. So when I have y squared, that should be y cubed, y squared minus 3 is equal to 0. So y minus the square root of 3, y plus the square root of 3. So the places in which these cross, if I were to draw it all the way out, draw this all the way out, is that it's going to cross at the negative square root of 3 when y is equal to that, when y is equal to 0, and when y is equal to the square root of 3. So its integration would then become, and I'm going to do it up here, I'm going to integrate from negative square root of 3 to 0. My most right function is the y cubed minus y, minus my most left, which is 2y dy, plus we go from 0 to the square root of 3. My most right function now is 2y, and my most left function is y cubed minus y dy. And of course, symmetry, so you could just do 2 times from 0 to the square root of 3. And the upper function in this is 2y. My lower function is y cubed minus y. Don't forget to put that in parentheses to distribute your negative through appropriately. Okay, so again, I'm just going to do a quick little sketch. This is, the first one is this. This is y squared minus 3. My second one, which is y minus y, I'm going to rewrite this as y and then y minus, I'm going to do it this way. I'm going to factor out a y, leaving me 1 minus y. So I know I'm crossing at 0, and I'm crossing at +1, so about right here. And it's a negative, so it's going to look something like this. So now I have to figure out where these cross. I need to figure out this point and this point, because the region I'm most interested in is right there. So I'm going to set these equal to each other, and so I have y minus y squared is equal to -3 plus y squared. Bringing the y squared, everything to the right-hand side, I'm going to get 0 is equal to 2y squared minus y minus 3. And then this factors, so I'm going to have 2y, y minus 3 plus 1. So my y values are 3/2 and -1. So you can see that my most right function is the y minus y squared. So my integration for this will integrate from -1 to 3/2. My most right function is y minus y squared. My most left function is the -3 plus y squared dy, and I'll leave that to you. Now, sine and cosine on functions of y. So if I were to draw the regular sine function, I would have said at 0, 0. And what I'm going to do is I'm just going to turn this so that I can, here's my pi, here's my 2 pi, here's my negative pi, here's my -2 pi, and my sine function would look like this. It would go up to 1 and then cross, then down to -1 and cross, and going in this direction, it's going to look like this. So here's my sine function. And basically all I did is I turned this to the side so that I could draw it a little bit easier, which still is not very pretty. Now the cosine of 2y is the cosine wave, but with a period of half of what it should be because of this 2. So it would start still at +1, and then it's going to actually go down, back, and cross back over. And it's going to continue to do that. It's going to go down, back, cross back over. Not drawn well, obviously, as you can see. Okay, there is my cosine of 2x. Now, they're telling me that I am going to go from -pi/2, so when y is equal to -pi/2, and they're telling me when we have y is equal to pi/2. So they're telling me where I'm going to restrict this. Now you can see from my poor drawing that it looks like right about here that we're actually crossing in there. And then from here to here we're cool, but from this point we're going to cross. So what I need to do now is I need to set these equal to the sine of y is equal to the cosine of 2y. So I have the sine of y, I'm going to get my double angle out, and this is going to be 1 minus 2 the sine squared of y. So I have 2 the sine squared of y plus the sine of y minus 1 is equal to 0. I'm bringing everything to the left-hand side. This kind of looks like 2u squared plus u minus 1, which we know factors. And so I have, let me see, I'm going to have 2 the sine of y, and then that's going to be a minus, and then the sine of y. This one's going to be a plus, this is going to be a minus. And so I have when the sine of y is equal to 1/2, and when the sine of y is equal to -1. So we know this is going to give us when we have plus 2 pi k, but we're not worrying about the 2 plus pi k. So I take the sine inverse of both sides, or I can just look at my unit circle, and this is -pi/2, which is exactly right here, which is what my graph was showing. Now this happens when I have the sine of y equals 1/2 is when I'm at pi/6. So this is the pi/6. So my integration then is going to go from -pi/2 to pi/6, and in this region my cosine 2y is the most right function. So the cosine of 2y minus the sine of y, and then I'm going to add to it the integration of pi/6 to pi/2, and in this region you can see my sine is the most right function, so it's the sine of y minus the cosine of 2y dy, don't forget the dy, and then I'll leave you to it to actually do the integration. Okay, so determine the area of the region bounded by the two curves in the given figure by integrating over the x or y axis, whichever seems the most convenient. So let's just talk about what each one of these is doing. Now this one, I don't have any graphs on any of these. So I would probably, go out to Desmos and decide which one is the most appropriate. Now this is in terms of x, so it is probably, without looking at the graph, I'm probably going to do this with a dx. This is in terms of y, so I'd probably integrate this with dy. Again, I wouldn't know until I actually went out and looked at the graphs, and we're going to do one or two of these. This one looks like it's already in terms of x, so I'd probably do this with a dx. This one looks like it's in terms of x, so I'd probably do this with a dx. And this one looks like it's in terms of x, so I'd probably do this with dx. Now I'm not really certain, so what I'm going to do is I'm going to go out to Desmos and I'm going to just graph these really fast. Actually, let's do C. I see I can just do without going out to Desmos. So this is a line that goes through +4 with a -3 slope. So this is y is equal to 4 minus 3x. And then I have the reciprocal function, which looks like that. So clearly this one is definitely a dx. I just have to figure out what this one is and what those 2 points are. So I had 4 minus 3x is equal to 1 over x. Multiply everything by x, I'm going to get 4x minus 3x squared is equal to 1. And then I'd solve, and then I'd find whatever my points are. And you can see by my quick sketch that whatever my a and b are, I'll leave that up to you. My upper function in this case would be the line 4 minus 3x. My lower function would be 1 over x dx. All right, so if I were to graph these other ones, let's go ahead and just go out to Desmos and I'll graph these and I'll bring these in and then we'll discuss which one is the most appropriate. And my first initial round on what one is the most appropriate is based on how it is solved for, but that doesn't necessarily mean that's exactly the way we're going to do this. So I went out to Desmos and I graphed x e to the x and y equals e to the x. And we're going from 0 to 1. So we're starting here at 0, we're ending here at 1. And this red one is x e to the x. This blue graph is e to the x. So you can see that we're going to cross at 1. So my integration would be from 0 to 1, plus they tell me that right here. And in this region, e to the x is the upper function, minus x e to the x is the lower function dx. Now this part will need integration by parts, so I just wanted to let you know that. So now I'm going to go out and do a graph of y plus y cubed is equal to x and 2y equals x. And I graphed the purple one here is the line 2y is equal to x, and the green one is y plus y cubed is equal to x. Now you can see from my graph that they're going to cross at 2 and -2. So I'd integrate, and this is symmetry, so I'd do 2 times from 0 to 2. And that's because it gives me this, and symmetry gives me the other side. That's why I multiply by 2. And in this region, the 2y is the upper function, or the most right function, and the most left function is y plus y cubed dy. Don't forget parentheses, so you remember to pull that negative all the way through. And so you can kind of see how to do these. I'm just going to do just e. This one, I'd leave this to you to do. I'm just going to look at e. Okay, and so for this last one, like I said, I went out to Desmos to get the graph. And we're going from -1 to 1. And you can see in this region, I didn't actually draw all of this. In this region, this is the cosine inverse. It's the upper function of x. And in this region, this is the sine inverse of x. So you would integrate from -1 to 1, or actually -1 to some a value. So I'm going to leave this as an a value, because we need to figure out where they cross. And so we'd have the upper function is the cosine inverse of x. And then the lower function is going to be minus the sine inverse of x dx. And then I am going to have from a to 1. And in this case, I have the sine inverse of x is the upper function minus the lower function, which is the cosine inverse of x dx. And then I'm going to leave this to you to integrate, and that's pretty much it for this video. It's really the hardest thing is to figure out who is the upper and lower or most right, most left, and finding the places in which they cross if they do. And so area between curves.